computer record. Okay, it's recording. Okay, now I'm gonna share my screen and then we can see who is accepting and who is not accepting. But let me see who else is. Instead, I'm admitting other people in. Okay. Now, I already created ECE3300 Spring 2022 group, right? Then we go here into CBB. Canvas. Courses. Announcement. Okay, so we have now 16 groups, right? Let's take it group by group and see what might be. Group 1. Peter, why you didn't accept? Did you receive it?
I'm not sure where to go.
Basically, no. You check your email that's associated with this account, and you will find an invitation.
Yeah, I got it.
You found it, right?
Yep.
Will you please accept it?
Yeah, I accepted it right now.
Let me see. Now we accepted, correct. And then we got a group 2. Setting. Both of you accepted, thank you. 3. Both of you accepted, thank you. 4. Both of you accepted, perfect. 4, 5. Okay, 5 is accepted. 6. Both of you accepted. 7. This one is not accepted. What's up?
I had accepted it from last time you did it.
You sure? Look. Say pending.
The name is wrong.
The name is wrong. So you're group 7, right?
Yeah. I don't know how. Oh wait, never mind. You did, it's in the. Give me a second. No, I did it for your lab. My bad. I thought it was the same one. It's the same name, just with 2 I's at the end. I don't have the link for the doc. Can someone put it on the chat, please?
We can cancel and do the game. I'm doing it in front of you guys, so at least we'll be sure that every single body in the system, right? So which one you are in?
The last one.
This one?
That one, yeah.
Accept, please.
Thank you. Check it up right now. There you go.
Accepted.
Thank you.
You're welcome. 8. Setting team. Thank you. 8 accepted. So 8, 9. Accepted. Both of you need to accept.
Oh, I guess we did it for your lab.
Yeah, you need this. The group is different than the lab, right? The course is different than the lab. In the lab, we just have experiments, right? Here we're gonna have a small project. Okay. So both of you, did you get the invitation?
I just accepted it, I guess.
Yeah. I saw it. Thank you. What about this one?
Really? It's here, I guess.
Give me 1 sec.
You find it?
Yeah, I'm just trying to find the email. Should be good now.
Let me see. Perfect. Thank you. 11. Thank you. Accepted. 11, 12. Perfect. 13. Both of you need to accept it. 13. Jimmy and Nash. Jimmy? Where's Jimmy? Hello? You guys are not here today, what? This two is not here, right? Okay, it's 14. Accepted. 15. Accepted. 16. Okay, so now everybody, except one group, right? There is group 14 or something, right? These two are not here today, right? That's what I assume. Okay, so what is the next step for this work? So I'm gonna share now my tablet. And we're gonna talk about, what is gonna be the next step. Then, we're gonna move forward to the lecture today, okay? Everybody can see my other screen?
Yep.
33 spring. Now, by tomorrow, I'm going to send to every single group a couple of topics. A couple of topics will be sent to every group under what Canvas announcement. Okay, you have up to coming Monday, which will be when, let me see. So this Monday, 14th, right? So gonna be 14th. So gonna be 2/14th, 2022. And 14th, every single group will be discussing what topics, and they will come with what? 3 slides. 3 slides. The 3 slides will be what? The topic. What is your plan normally in general? What you're gonna do is, and the third is gonna be what, like a Gantt chart about, you know, what is the plan to execute until you will be done with this what topic. So far so good.
What was the second slide, Professor?
So one gonna be talking about, you know, what is the topic, right? So let's say that, you know, we decided as a group to select this topic out of the 3 topics or 4 topics you already give it to us as a group, right? And what we fully understand about this topic, we already found in internet this and this and this and this and that, right? And, you know, you can put some information about example, right? Let's say that I tell you that, you know, implement, right? X algorithm using Verilog on FPGA, right? Then you will search in internet, what is this X algorithm, right? And who implemented before? And how did you implement it roughly? It doesn't need to be like perfect, right? And you will have like it's not like complete Gantt chart, but at least, you know, like a framework of Gantt chart telling me that, you know, what is your strategy? How are you gonna implement? It doesn't need to be like completely perfect, right? But something can be refined week by week, right? Saying that, oh, we are planning, for instance, to collect this information. Oh, we are planning to do this. Or we are planning to use the syntax that we learned from this week and this week to implement this part and this part and this part. Is it okay? Sounds okay, or is it a little bit confusing?
That sounds good.
Okay. Normally, what type of project actually I ask for? You know, there is a bunch of stuff in this board we have. It's called communication protocol. One of them UART. One of them VGA. One of them Ethernet. One of them HDMI. You already have also, beside that, we have what? Switches. We have buttons. We have LED, right? We have colored LED. We have PMOS. You see those? Normally, what I'm gonna do in the middle of the lectures while I'm moving forward, I will tell you how to work with UART, like, you know, RX, TX, like, you know, sending data from the computer to the FPGA, or, you know, sending data from the FPGA back to the, you know, computers. That's called RxTX, like a transmit and receive, right? Then, you know, I'm gonna also give you some information about how can you work with VGA, and, you know, how can you even, you know, send data from the FPGA to the VGA to present it. We already played with the switches, if you remember from the last lecture, right? When we made this full adder, and we start like, flipping the switches on and off. While we are moving, forward, like week by week, we'll start using it more and more, right? And we start building complicated circuits, right? We already turned it on and off some LEDs, right? Also 7-segment display. I will try also to talk about this in the middle of the week, and then you can guys start using it with lab assignments. You will hear it from here, hear it from there. How you're gonna be even write a Verilog for it. So these pieces will be ready with you by the end of the whole entire semester, right? You will be able to put pieces together, right? And these pieces together will make like a picture. Like for instance, I will write some switches on algorithm. Those algorithms will be encrypted. Then, the data will be presented on VGA. Or, I will take data from the computer, send it to the algorithm X I already implemented on FPGA that will be presented in VGA and so on. That sounds okay? It might look hard now, right? But it shouldn't be hard. Because, I assume all of you guys are looking for internships, right?
Yes.
Soon enough.
Exactly. So it's better for you guys to have something like this by end of this semester, by end of this course, you will have it posted on the GitHub. And I will help you to post it on the GitHub. Why? Most of the companies looking for skills. And, I want you to use the skills. One, code readability. Like people will start reading your code. Also, code representation on GitHub. This is something very important. IBM, Qualcomm, Intel, even startup companies around here, they will tell you, can you please show us samples of what you already have done on GitHub? So what I do normally in your resume, you will put a QR code in a very nice spot in your resume, right? And that will be connected to your GitHub that you already have, right? That will present your work. So the manager will come to you your resume, right? He will just scan the QR code in your resume. Automatically, it will pop out for him what? The GitHub. And I will show you in the middle of the course how can you put like a video, you put whatever in a way that it will look really, really fancy. So then you will just be selected. Sounds good?
Sounds good.
Okay. One of the important things that I would like to mention here, right? This course, we are not inventing something new. We know that there is digital circuit design, right? We are aware of the digital logic design in 2300. You guys agree? What we are doing, yeah, go ahead.
No, I was just responding.
Yeah, what we are doing in this course is basically we are writing syntax to describe whatever we learn in 2300, right? Pretty much.
Yeah, it's like its coding component.
Exactly. And also, complexity. Like, how can I, instead of just build decoder encoder, how can I build a bigger circuit consist of these pieces to do something, right? And how can I test whether these things is working or not? Do you guys agree?
Yep.
Okay. Any question regarding this subject before we move forward to the next part? I like to be slow, but efficient. So now so far, before I jump out of this area, if there is any concern, something is making you a little bit afraid or like hesitates, or something, let me know so I can clear it up. Tell me.
Wait, Professor, I just wanted to clarify. So for the slides, the first slide is basically
we describe what the topic is that you gave us. And then the second slide is an example of the topic. And the third slide is the chart.
The Gantt chart, yes. If you want, I can write it down here clearly, right? Slides needed by, when I said it will be, February 14th, right? Bear group, right? One, first slide, right? Of course, your name, right? Correct? They're gonna be a list of your names. Two, they're gonna be slide number one, right? Two are gonna be which topic you decide out of topics I gave you. If any of these topics you don't like and you have another topic in your head, go ahead and present it. Here, look. If any of my topics didn't click with you, feel free to introduce your idea. So far, so good?
Yeah.
Okay, now, second slide. In the second slide, whatever you collect about the project, you select, right? Then rule of every member per group. So for instance, I'm group A, right? We have two friends, two partners, Taylor and, Joseph, right? So I would say, we decided, Taylor will be working in this and this and this and that, roughly. Joseph will be covering this and this and this and that. The key person, like this, also define the key person per group. Like, I decided, Taylor, for instance, that's between you guys. Taylor will be the person will be representing, or, he will be doing this in terms of presentation. I will be the care of writing this report and whatever. You know what I mean? So try to distribute tasks between of you guys inside the group. Sounds good?
Yeah, so basically we just say what each group member did for the slides.
It's not the slides. What are we gonna do in the project?
Oh, for the project. So we're selecting the project. Okay.
Mhm.
Oh, wait.
I want to be fair with everybody because nothing against anybody here, but I know sometimes, I'm not talking about you guys, but I'm saying sometimes one of the group member will be doing homework. I was a student and I have seen this many times. Honestly, my group was dumping everything on me. Anyway.
What do you mean by key person?
Like, a person that will be like acting the manager of the group. Like, the one will be collecting pieces, right? So normally in the company, in a company, I was working for Atmel. You guys heard about Atmel?
Yeah.
So Atmel now is a part of Microchip, right? We, my team was the team who built Atmega. So the one in Arduino. We were 5 designers, right, in my team. I was the R&D guy in the team. I was the one who told them what they do. The other we were just writing code, right? So the whole entire idea now, one person out of this group will go into the manager, the higher level, right, and say that we have done this today. That was the work, and we done this work, done this one, done. We are missing this and this and this, and then we are in the progress of it. roughly that will take this amount of time. Make sense? That's the job of the keepers. Okay?
Yeah.
Okay. Now the third slide, right? Third slide. That will be consist of what? The Gantt chart. Gantt chart, it's a way that it will tell me, oh, I will work in this week, this week, this week, this week, this week. Oops, we're gonna finish this project on time. Then, you know, from time to time, you know, something wrong happened in this week. It's not allowing you to finish the part, right? Then you know what you're gonna do. Either that, you know, you have to tell me what is the problem, or, you know, either that, you know, you're gonna push it into the week after and so on. So by this way, you will not come into like this, you know, the deadline for the submitting the project is tomorrow, right? And then, you know, you decided to work on this project 2 days before the deadline. Project will fail, right? Will be too much stress on you also. Do you agree? But if
Yeah.
you break the algorithm into pieces, right, and every single, you know, every single week you are finishing module, right, what will be the consequence? You will finish on time. You might even finish earlier, right? Do you agree?
Yeah, I think it's smart for projects.
I mean, this is basically what we learn. Oh, okay. Any questions so far regarding this specific part?
Yes, just one quick question, Professor.
Yes, please, go ahead.
So the Gantt chart is pretty much kind of just the timesheet that we're going to be following, or we're going to be filling out, right?
Yes, sir.
Okay.
And it's roughly can be changed. You can, let's say that, you know, after you made the presentation with me next week, right? You started reading more and more, right? Then what happened? You came and found that, you know, what you read now, it's need a slight modification, right? There is no shame. Go in your Gantt chart and change it.
Is there a deadline for this project?
You guys, you forgot syllabus? Did you guys look at the syllabus?
Yeah, but I don't remember.
Okay, you know, there is no problem. I will share with the syllabus, you know, well, you know, I'm here to help, right? So here is the syllabus. Syllabus guy. Here, right? This ECE3300 syllabus. Where's the syllabus? Module. Syllabus, right? Here, projects, 10%. May 3rd, every single group will submit the following package under the designated GitHub repo. Per each group, group members / repo will be generated by the professor. So I already generated the groups, right? And I'm in the process to give you the topics, right? So in May 3rd, we'll be submitting whatever. So in the middle of this, I will tell you how can you submit and what type of documents need to be submitted. Because it's in the progress, right? Make sense? So for instance, your presentation you're gonna make on this coming Monday, right? The document of the presentation, where you gonna post it after you finish? Under your GitHub repo. Make sense?
Yes, Professor.
Super. Any questions so far? No question? Or there is a question? Tell me. Is it an actual presentation? Yeah, it's a presentation. Yeah, you're gonna go and present it to the groups. So I will dedicate some time in the beginning of the lecture. We have 3 hours something, right? So in the beginning of the lecture, let's say group number 1, you have 3 here. You have 3 to 5 minutes to present your slides as a group. Okay. Why I'm doing this? Because maybe some other members of the other groups will have even a creative idea that will help you. So you can take their feedback and apply it there. By the way, the list of the project per group, it will be in the announcement, right? So everybody can see it. It's cool for you guys to know what's going on,
What kind of projects have your classes done in the past?
Huh?
What kind of projects have your classes done in the past?
Infinity. All of them crypto. My background crypto, But I can give you some other stuff, don't worry. I will tell you something. A couple of years ago, actually, they built almost like a PlayStation. Can you imagine?
Whoa, really?
Yeah. We were playing games in the lab before the pandemic.
Wait, so I wanted clarification on are all the projects going to be centered around the Nexus board or anything?
I mean, we should be Nexus 4. I mean, that will be fair enough for everybody. Unless there is something board it's specifically you need, then I will give it to you.
Okay, so our projects need to use the Nexus board.
I mean, because this is what you have in your hand, right?
Yeah, okay, just clarifying things.
There is no need for you to spend money, basically. But if I find something more fun and you guys will agree, I already have a lot of boards. Okay? You will lend it, you finish, and then you will give it back to me. Something like that. Okay?
Sounds good.
Super. One thing I need to mention before we close the subject, right? The way that, the final report will look like, you don't need to think too much about it now, but, you put it in your consideration. It's going to be like an IEEE format. I'm not sure if you heard about this before. Have you heard this term, IEEE format?
No.
That's something you're going to learn with me. So you're going to learn IEEE format, and I will encourage you guys to submit this into conferences, and I will find a way to pay you to present this papers in the conference. Under something is called travel grants for IEEE. Why I'm doing this? Somebody can tell me.
We want to do research.
It's not research. I would like you to present yourself in front of the future employers who will be attending these conferences. So your chances for having a higher job is really high. It doesn't need to be like, we're going to build tomorrow a satellite, right? You guys know what is the #1 undergraduate research institute in the nation? I'm not talking about PhD institute. I'm talking about the undergraduate. So it's an undergraduate program, and they do research. #1 in the nation. Can you imagine where?
Is it Caltech?
Caltech is a PhD granted institute. It's like their mission is research. No, the undergraduate #1 top undergraduate school in the nation is the U.S. Air Force Academy in Colorado. Guess the undergraduate cadets, like you guys, basically like students, right? They launch satellites. And even they design rockets out of their courses. Can you imagine? We are better than them, right? So we should show them that, you know, we are creative, right? Sounds good?
Yes.
Huh. One more time. If there is any problem so far with the story that I mentioned, no shame to say any question. You can ask me the questions. We need all of us to learn. We are one family. So you tell me what is the problem. Is there something not clear? I can clear it again so we can move forward. Huh.
So just double checking, you said that the presentation is in front of the class, but the one where you encourage us to go to the IEEE thing, that one's voluntary?
Wait, again, the presentation that's gonna be between us, right? I'm talking about here the final report, that's gonna be submitted in May 3rd.
Right, you said you'd encourage us to do it in front of the IEEE thing. So encourage
Not
means
making
that's
in front of
voluntary, right?
IEEE. It's not making.
Okay.
We're gonna write a paper about the project using IEEE format, and we will submit it to a conference, which is one of IEEE undergraduate conferences.
Oh, okay.
To present. That's our final product. Make sense?
That clears it up, thanks.
Any other questions, guys? So that's why I would encourage you guys from now on, every single group, to look into IEEE what? Travel what? Grants and internet. Because they pay you money. Do you know that? They pay you money so you can go and present. So it's not bad for you to be paid, right? So if I'm you, I would say that, oh, from February 14th, I have this idea, right? So, you know, maybe I can search about this and this and this and see, you know, which conference I have to put my eyes on it. And then, you know, how much, you know, I can get out of it. I fill the form, send it to me, I sign it to you as a professor. So, you know, IEEE will pay you. Make sense? So you plan, keep planning. 99% of the job of engineering planning. You know that? It's not just like, you know, attending course and taking some grades. You just plan. Sounds good?
Sounds good.
Perfect. Move forward to the next topic, or still there's some more questions? Move forward? Okay. Now the second topic. Do you have any question from the last lecture?
Is the lab included with that?
No, lab for lab. You know, let's focus on the lecture, right? If we have more time, I can talk about the lab. Go ahead, Taylor.
Please.
I had a question because last lecture you were going to go over the test bench for the like the for loop generate.
Sure.
But we didn't end up doing the initial test bench.
Sure. So you would like me to revisit the test bench, right?
Yes, please.
Okay. Who else would like me to look into what other aspects? Huh?
Same thing, the test bench, like how you would test the n-bit ones.
Definitely. We're gonna even build a lot of test bench today. Huh?
Perfect. Are you gonna go over how to set it up with the board?
Sure. So you want to set up the board, right?
Yes.
What else? Huh?
Professor?
Yes, sir.
If you did this last time, but could you also go into a little bit of the RTL analysis, maybe like the elaborate elaborative design.
Sure. What else? Any other thing that we need to talk about from the last time? Because that's gonna be repeated every week. I'm gonna repeat it. Excuse me. So let's take it topic by topic. Taylor said this bench. Majority of you said this bench. So I'm gonna now turn on my wait a second. Close this and stop sharing. Then we're gonna go into sharing my Vivado. Okay. Share Vivado. Vivado. Everybody can see my Vivado?
Yep.
Yes, we can.
So Vivado is, that was the project we worked last time. So we know that recent projects is basically whatever we already have done. You just need to click on it, it will open, right? So it'll take some time because my computer is the fastest computer in the nation, Oh my Lord, again, the times. Oh, it opens. Can you imagine? Anyway. So if you remember, last time we built one bit full adder, right? And then we built a test bench for this one bit full adder. Do you guys agree? Then we used a for generate to make a flexible parameterized full bit adder, right? Which is consists of one bit full adder replicated, correct? Then we tried to test it and we build a test bench around this full adder, right? Everybody agreed about that?
Yes.
Okay. So build a request of majority of you initiated by Taylor. Let's say that, I decided to look to one bit full adder, right? And here's one bit full adder. I clicked on one of them because they are the same, right? And did you see this three stars in the top of each other? That means, this is the top design I'm looking for, right? If you look carefully here, you already have what design source, you have constraint, and you have simulation sources, correct? So if you look into the design source, that means I'm looking for the RTL, that means the set of Verilog written that will end up being placed on the chip. That means it's gonna go on the FPGA, right? We look into the code. We said, from the slide that I shared with you before, there is 3 approaches to program the FPGA, right? One is what? Git lib. The other one is what? Structure. The third one is what? Behavior. Do you guys agree?
Yep.
Okay. Gate level, we said is easy busy lemon squeeze. We just sort some gates together. We like what we did with 2300, that it will build a block, and this block is what have bunch of input and outputs, right?
Right.
So we learned that the module is basically the chip we buy from 2300, like the TTL chip, like the chip for 7-segment display, chip for the decoder, chip for whatever, right? But we write the code for that chip that describe the relation between input and output, right? So here, process-wise, we build something that's called module, and we give a name for the chip. So this chip is gonna be full adder, right? And between these 2 parentheses, we already sorted what input and output ports, and whether that every single input or output, is it single bit or multiple bits? Do you guys agree? So far, so good?
Yeah.
Super. Now, what are relation between of them based on the circuit we built in 2300, right? Which is XORs going to be carry a sum, bunch of AND going into OR, that will be the carry out based on the K-map plus, truth tables and whatever, right? And we already did that, right? In this particular part, any question? Christopher, Joe, David, Taylor, there is no question or there is question?
No questions.
No
You-
questions,
you-
yeah.
Yeah, you guys already digested this idea about, I need wires and we connect wires or not?
Yeah, yeah.
So it's clear, right? Okay. Now I need to know, maybe I made a mistake and this circuit is not full adder, right? So what is the only way to do it? In the 2300, you used to bring the breadboard, do you remember? And we put, you put the pins in the holes, right? And you start having wires connected to the input and output. And then you put here some of the wires going into the oscilloscope and some of the wire will be going into the generator, right? Then you start pushing input and you look into the oscilloscope to see the output, right? That's what we did, right?
2300 lab,
Yeah.
not on Zoom.
Who was giving you 2300 lab?
Can't remember the name.
Not trying.
If I was giving you the 2300 lab, Zoom stop being silly now. Can you hear me? Hello?
Yeah, we can hear
Yes.
you.
we could hear you.
Yeah, because it got breaking. I saw myself like moving slow, so I was like, what's going on? Anyway, so there is something coming from analog devices. Have you guys heard about a company called Analog Devices?
Yeah.
They already were selling like a portable oscilloscope. You can have it at home. You connect it to your PC and it will work like an oscilloscope for $200, something like that. And you can do all of your 2300 lab almost like you're sitting in the lab. Do you know that? You have the ICs, breadboard, then you connect the wire into computer, then your screen of the computer will turn to be oscilloscope. Then you will take another USB, connect it into your breadboard, then it will be like these generators. I'm not sure if you guys have heard about that or not, but anyway, if not, I can show you some stuff. Anyway, now, what is the similar thing that in Verilog look like the breadboard? This bench, right? So the process of bringing the IC by your hand and put it in the breadboard holes is called what in Verilog? Instantiation. Okay, so first of all, you have to create the container of the test bench, right? So if you don't have it, you go in add, right? And then you select what? Add or create simulation. So far so good.
Yep.
When you did that, it will give you like your building design source. In the test bench, be sure that there is no input or output ports. So out of this, if you go into the files on the source here, you open the simulation, you click there, you open, you will find what it created to you module like the RTL, right? But I call it what FA_TP. So far so good. And you will find those two parentheses. It was in the normal RTL, right? Here, between of them, nothing. Make sense? This is the first part, which is creating the breadboard. Now, instantiating, that means, calling that IC to be inside the board, right? You have to do this process, which is what? Calling the full adder. The full adder has bunch of wires in and out, right? But I cannot call it with its name. I have to call it with a name because I can have million of full adder on my breadboard. Now I call this IC COMB1. So this IC COMB1 is basically a full adder. Okay? Sounds good to you, Taylor?
Yeah.
Now, I need to have bunch of wires and, pushing something inside that IC and some of wire taken out of this IC, right? So basically, since I play with the input that is going inside the IC, it has to be what kind of storing information, right? Because I have two things that in physics, right? Either that's a wire or some storing information, right? Input can be changeable. Wire, you cannot change values in it, right? So in that case, I make those inputs as what? Register. Sounds good? And I connected them into the places for the input. So far, so good?
Yeah, Professor, I have a little bit of like a side question, but it's kind of related. So if we wanted to make a value that is operated on, so say it's multiplied by something, would we make it like a parameter if it's like a set value, or would we make it like a register?
Okay, parameter is dealing with what? This level of design source. Parameter is not going inside what? Inside the design simulation. Parameters, it's just a value to replicate components.
Okay.
Make sense?
Yeah.
Yeah, so
Yes.
it's only when we do our for loops.
And I just need to say something to Taylor. Taylor, there is something else we're gonna learn. It's called define. That can be used later on. So you can define like a constant value that you can put it inside the register. Okay. Then it can be used in a test bench.
Okay.
Okay. But for now on, when you are using parameter end of the day is something to change the replication. Instead of by your hand, put component, and connect them by your hand. Better for you to do what? Automation. Sounds good? Okay.
Yeah.
Yeah. Now I need to see the output of this component or module called full adder, right? So I have to connect it to my what? Oscilloscope, right? Do you agree? What is the oscilloscope in this case here? What form? So far, so good?
Can you repeat that last small part?
Okay. The IC full adder has an output, right?
Right.
How I'm gonna see this output?
The oscilloscope.
Exactly. I don't have oscilloscope here. So, but oscilloscope for the Vivado is what? Waveform.
Got it. Okay, that's what I missed.
So that's why the two outputs, see those two outputs are wires, because end of the day, they are just passing something. They're not storing data, right? So that's why, rule number one, when you are making the inputs to the test bench, it has to be registered. The output will be wires. Good?
Good.
Have you noticed something? Those two guys are hanging here. They are not connected to anything. Do you guys agree? They're just coming out of those port and that's it. There is nothing here in initial about them, right?
Yeah.
Later on we can have, but at least now we are just hanging them like this. Why? Because they are already connected to the waveform. So far so good?
Yes.
Now we need to apply into those wires connected to the input some values so we can see what is the reaction output, right? So we use two different techniques. One is called always, one is called initial block. What we are using now is called what?
Initial.
Don't worry about this, somebody's calling me. All right, so initial block, it is a kind of what? A snapshot of time. Like, I would like to set this input with these values, one time shot. Then I put it inside this initial block. So far, so good? Okay. But if I would like to add the time in the middle, what I can do, I can set up the input, set up delay, set up different input, set up delay, set up different values of the same input, set up delay, and so on. So far, so good? So now, how to define it? You write initial, as you can see, and those parameters in the middle that's changing inputs and input values, it will be between begin and what? End. Okay. Now How many inputs we have for this IC, Taylor?
We have 3.
Perfect. So that's why I put 3 every time, right? Do you agree?
Yeah.
Then, you know, I'm asking in every amount of time. I lost this. Calculate them later. Anyway, so, you know, 10 nanoseconds. So, you know, to add a delay, you have to do what? This sign, and you put the value of the delay. And that value will be in nanoseconds. So far, so good?
Yep.
Okay. So now what I'm doing, I'm saying that, you know, apply these values into the inputs, and then, you know, change the time, apply these values in the input, and after this, change the time, change the time, change the time. But, you know, and then, you know, I said, you know, after that, stay 1,000 of nanoseconds, and then you what? Close my oscilloscope, which is what? The waveform. Right? So now what I did, I basically prepared the experiment on this IC in the test bench environment. Now I need to what? Push the button so I can see what happens, right? So what I did now, I put all possibilities of the experiment, and it's a time now for me to run the experiment. That makes sense?
Yes.
Okay. Run the experiment. I have to go in what? Simulation. And there is run what? Simulation. If I click on it, it will give me different level of what? Simulation. The current one we are learning is called what?
Behavioral simulation.
Behavior simulation. That means, you know, I'm checking the behavior of the code I wrote because nothing on the chip yet. Right? So I will run here. The rest of those guys, I will take them one by one to you. Okay? It's not in the syllabus, but, you know, I'll take care of it because, you know, SpaceX interested in these stuff. Run behavior. So now what's happening is running the analysis. Christopher Lay, right, is running all possibilities of the analysis you already set it in the initial begin end. Okay?
Yes.
Let it run. I need to go 1 second here, you know, and I'll back to you. Just keep it running. Okay, guys, it open. So if you look now, my oscilloscope is what? Ready. Do you guys agree?
Yep.
Here is, you know, but I don't see anything. You know why? Because I use it multiple times in a different purposes. So to see what it should happen, I go here. Can you see the side? Objects. And there I select all different in and out ports for the test bench. Right? Which is connected to whatever happened. So how can I do this? Look here. There is here, it's called scope, right? And is looking into the FATB as the top file. Do you guys agree? So that means looking to every single signal under the name of the FATP as a test bench, right? But what about if I would like to see internal signal inside my chip? What should I do? I can stop here. You see that? When I stopped here, it gave me all possible signals it was inside the design I was building. You guys agree?
So the top one just gives you like input and outputs.
And input, no, it gives me the names of the input and output of the test bench.
Meaning like,
package.
so meaning like the whole as a block, right?
Yes, here, see those.
And comp one will give you what the values of inside the block.
So what is comp one? It's a full adder.
Correct.
You agree? So give me what is happening inside the full adder.
Just pretty much everything you have in objects, right?
Basically the internal wires.
Correct.
Everything inside the chip.
Correct. Just like wires in all the gates.
Everything we have done.
Correct.
From passing to passing to passing to passing. So this is very important to know that, so you can, while you are working with complicated design, to debug. Oh, where is my mistake? Oh, it should be here. Oh, I catch it. Then you return it back to your RTL, you make it changes, then you will run again simulation and you catch it. So what is the benefit from the test bench from your point of view, guys? Huh?
Maybe it's to check if your circuit is right before putting onto the FPGA.
It's not print, it's basically deploying the stream on the FPGA. The study said that if you go ahead and run every time to dump on the FPGA, you're gonna take 50 minutes, 20 minutes, 30 minutes, 1 hour. Sometimes some design take days if it's really huge. Okay, in that particular case, you will never finish your task. So it's better for you to do a test bench. Then you will just run one process of synthesis and routing to deploy in the chip. Do you agree? So that will save you a hell amount of time. So this tools is help and assist you to catch errors before even you will generate the bit stream that will be deployed on the chip. Sounds reasonable?
Yeah.
So which one we would like to see, guys? The comp or the FATP?
FATP.
Okay, so in that case, I'm gonna take those guys and see, I already selected them, right? I highlighted all of them. Then with my cursor, I will do what? Move them to what? Just grab them.
Drag them over.
Exactly. I can just say save. So I save it in the file is called WCFG. If I run another simulation again to the same component, this will be coming to me. Okay, now nothing in front of me, right? Why? Because it's already run in the past. So in that particular case, I will go in what? Look at this. I restart. Did you see it? Control plus Shift plus F5 at the same time. So you can just say what? Restart. So now what? I initialized. Then I can just go and I say what? Look, run all. Boom. What happened? It closed the simulation because it passed already the 1,000. So you can just jump here back and you would like to see what's happening. Look here, zoom fit. So what is showing me now, it's showing me all of the possibilities that I set it up in where? In this initial block until I close. You guys agree?
Yep.
And you can just stop like this. And with holding your left click of the mouse, you can just change the zoom. See? Or you can stop and control and the roller in your mouse. You can just zoom in and zoom out. See? Boom, boom, like this. And of course, here is telling you what the time and what happened with the time. Time travels, right? 0 nanosecond. All of them were zeros. 10 nanosecond. I asked, the pen to be high and this low and this low. Consequence, because I was adding 1 plus 0 is going to be 1. There is no carry out. After 10 nanoseconds, I asked this one to be 0 and this one to be 1 and this one to be 0. So the output was what? 0 plus 1 plus 0 is 1 and there is no carry out. Then in this particular case, I asked all of them to be 1. So I'm actually assuming that my output, these two guys, will be what? Will be 1 and 1, because 1 plus 1 is 0, and you have 1 carry out plus 1, it's gonna be 1 and 1. So then I move forward. Then there, I asked 1 and 1 and 0, right? So 1 and 1 and 0 is basically 1 plus 1 is what? 0 as an output, but the carry out is 1. But in that case, I asked this to be standing for 1,000, so stayed as it is forever. Does it make sense to everybody?
Yes.
Okay, Taylor, any questions so far regarding the test bench?
No, not so far.
Okay, anybody else have any problem with the test bench?
I don't have a problem with the test bench. I just right now you did something where you highlight all the objects and then you drag them into name, right? It doesn't let me do that.
Wait, when you do this?
Yeah.
But did you see I already highlighted, right?
Yeah, how do you highlight them?
Look at my mouse here, right?
Okay.
I already highlighted, right? You can look into the screen and my mouse movement, right? Here in this left, right?
Okay.
I grabbed it like this. So I stopped on it, and then I take the execution of the mouse here, right? And I left it like that.
Yeah, it doesn't let me. It has like a little like circle with the line across
Which
it.
version of Vivado you are using?
I think it's like 19.2.
It should be fine. I would recommend everybody to go with the same Vivado. So
I do have the names do appear like automatically. So when I run the simulation, the names automatically pop out on their name. So everything's good. I just want to know, like, in case that we need to drag the names again.
See what I'm doing, right? I stop here, right? Right. Let me take this, right? I came here and I click on one, then I take shift click, and then I continue this. So I took all of them, then I just go into like this and then grab more.
Oh, there you go. Okay, thank you.
Work?
Yep.
Perfect. Anyway, so far so good. We finished the test bench as it should be, right? So
I just got one question. I know you answered it already, but
no, but that's fine. If there is anything, please tell me. Go ahead.
so if you click on the FATB, that's going to give you all the ports. And if you click on comp 1, that's the internals, right?
That give me all the ports input of the FATB, which is look here, look. FACNTB, FA port ATB, FA port BTB, FA port sum out TB, FA port C out TB.
So not the outputs for the actual full adder.
Huh?
But
those connected to the outputs, right? Because I connect them here, right? It's like wire. Do you remember the wire when we take it and connect it to the pen? Now this is representing the pen, right?
okay, so you get the same output, is what you're saying. Okay.
Let's go into this, right? Comp 1, right? FA, right? Look, it came into FACN, FA port A, FA port A, FA port B, FA port B, FA sum out, FA sum out, FA port count, FA count, right? Then look, FA XOR N, it came in a different color, right? Why? Because this is the wire. FA N1, FA N1, N2, N2, N3, N3, for N initial. That's it. Is there anything else as a data or wire is connected into this? No. So we basically cover everything. So you can draw in front of your whiteboard the circuit, and you start looking into the behavior in the waveform and see, oh, did it give me what I want here? Did it give me whatever I want here? Everything looks perfect. Move forward.
Will there be any time or instances where we might have an extra object than what we have in the code?
Everything is covered here,
So everything it will match the inputs and outputs, right?
Period. Yes. Okay, any other questions? What was the second question? It was about set up the board, right?
Yes. And I also believe they asked to see if you could run the NBits version.
Yeah, let's go for the embed version. That's fine. Okay, so embed version, right? So we can stop simulation. See, it's here, say simulation, behavioral simulation, whatever, right? I can just go here, look, close simulation, buy simulation, discard simulation. I don't want to save it, right? Gonna take some time, sorry about that. Close it, right? Now, out of the 1-bit full adder, luckily I found it like concurrent, right? So, I take one to the other one to the other one to the other one, right? So what I did here, I already came into another module I created, and I call it not this, I'm sorry. I click here and I call it FAN bits, right? But this FAN bits, it has to be the top design. It doesn't have these 3 dots and one in the green in the top, right? Do you guys agree?
Right.
So in that case, I will click right and say sit as what? Top. Takes time. See, it's updating you, right? What happened here?
Set as top.
Exactly. Now, simulation. Which one is actually the one is active? It's FATB, it's just single bit. So basically we have to go here and also do the same thing for the simulation environment. Super. So now we are in the same page that, we are selected the right RTL that will be tested with the right test bench. So far, so good?
Yeah.
Okay. Now let's go into the FANT. We learned that there's 2 different things from the simulation, from the slide that I shared with you last time, that there is 2 different way of flexible, instead of you add component by your hand manually. And this is called parameters or local param. You guys remember that?
Yeah.
And we define differences. Parameters, it means that, when I will instantiate, I can change the value that it was initialized in the block itself, right? So I can have this children and, parents, leaves in the data structure, right? Same story. I can ask the module to come on my new top files. Oh, you already have another problem. Okay, that's something. Okay, and then, and then I can change this value automatically. It will be remapped into whatever number I want. While local param, you cannot it shouldn't be overwritten. It will not allow you to overwrite values coming from the module. So which one we use for flexibility from your point of view? Parameter.
Yeah.
But still, when you build a chip, use a chip, like, while we're doing, while I was working for Appman, most of our job, it was just like writing code like this. Okay. So sometimes there is a job for local param. It's better for you to do it, which is basically when you design memories. Better for you if you would like to specify a certain area in the memory. You don't want to make it flexible. It will have a specific architecture to use local param. But we are not into this now. Okay. So better for us to learn now one by one. Parameter. Sounds good? How are we going to place this parameter as a syntax inside the chip, which is the module here? Do you remember this sign? We use it for the simulation and we put the value, then it's going to be delay.
Mm-hmm.
No, there it's different. We have to make 2 parentheses and then, we put here parameter, you put the name of the parameters, and then, you put the value of the parameter. So if for full adder, this is not even variable now. It's a logic thing, right? What is the difference between 4-bit full adder versus 8-bit full adder?
It's the amount of inputs per.
Exactly. The size of the operand, right? The size of the A or B. Is it 4-bit or 5-bit or 6-bit or 8-bit, right? So that means the number of wires inside the operand, right?
Mm-hmm.
So that's why I call it data what?
Data width. Okay.
Exactly. Okay, then we start defining our input and output. So we close this and we don't have any semicolon or anything, right? Then we open a new what? Open a new close what? Port mapping, which is input and output ports. Now input is called what? Carry in. The multi-bit full adder, it has single bit carry in. Do you guys agree?
Yes.
Then it has multiple bits of the A, multiple bits of the B. And of course, the output will be multiple bits, but the carry out is what? Just single bit. Make sense? Why I'm doing this? If you remember when we said defining the registers or wires or the input and output, we said they're gonna be what in parentheses, and we say data width -1 to 0. Why? Because number of wires is including 0. So let's say that I want 8-bit. 8-bit, it should be what? 7 to 0. I want, for instance, 16-bit, it's gonna be 15 to 0. You guys agree?
Yes.
That's why I said data width -1. Because total for me is 8. But if I put 8 0, it's gonna be 9. Do you agree?
Yep.
Okay. Now, imagination. How did you build a 2-bit full adder? It's basically 1-bit full adder, and the carry out of that 1 bit going to be carry in of the second one, and then you will get the output to be carry out, and the sum and sum, right? Do you agree?
Yes.
Exactly. So that's why we came and say, imagine I have n bits full adder. That means I have in what? In carry out. Right? Then we're gonna thread them in between input and output. Do you guys agree?
Yeah.
So that's why I made a new wire. It's called bridge. So far, so good.
Yes.
Then where is the 1-bit full adder we need? So we instantiate it, and we call this IC what?
Unit 0.
Unit 0. So instantiate it to build what? The first unit of the in bits. Do you guys agree?
Yes.
And here is the thing, right? We connected the carry in, the first bit of the A, the first bit of the B. It will bring me the first bit of the sum. And of course, the carry out, it will be what? The first bit of the bridge, right? Then I use something for flexibility. It's called what? Genvar. So what is Genvar? Do you remember in the C, when we are actually making for loop, do you remember what you used to do? We say for, and then we say int I equals 0, right? So basically we define the I. Do you guys remember that?
Yeah.
So defining the I use what? Genvar. Generate variable. So genvar is called what? Generate variable. And I'm gonna make this variable integer. Sounds good? Then I start using I would like to generate blocks. That's why I call it generate, and I close it with end what? Generate. That's a syntax. You have to know it. Okay? Then inside the body, there is a for loop that will what? Connect between block until you will build the thread of the in-bit full adder, right? Now I build the first block, right? I need to build the rest of the blocks, right? So far, so good?
Yeah.
Okay. Look what will happen here. So now I is equal 1 to I data width, and then the I will be incremented by 1, right? Then I have the blocks here, right? If I put I is equal 1 in this communication, what will happen? I minus 1, that means 1 minus 1 is what?
0.
0. So that means this block is connected to what? Bridge 0, which is correct. That means the second unit will be connected to what? 0, right? Because the carry out is 0, it's going to be carry in for the next block, right? Then this is what? A1, B1, right? Then the output will be what? Sum 1, right? Then the bridge will be what? Bridge 1. Then you know when I is equal to, what will happen here? 2 minus 1, right? So that one, it was carry out from the second block, will go what? As a carry in for the third block, and you will move forward. Does it make any sense? Or should I draw it in front of you?
I think it makes sense.
I want to be sure that everybody it makes sense for them. So anybody has any problem so far?
This part's pretty much just conceptual of the full
Yeah,
adders.
that's completely out of the 3300. It's basically 2300.
Yeah.
But by the way,
I had a-
yes, go ahead.
I had a question about the test bench on the end bit though. There's a couple things where you call in the parameter from this one that I didn't understand.
What happened to me?
On the test bench for the end bit, you called in the data width for this file.
Oh
and
yeah, I will tell you.
I didn't get that.
Yeah, so David, do you remember when I told you in the parameters you can overwrite what is written in the module?
Yeah.
So basically, you know, in the test bench, what we are doing, we instantiate. Do you agree?
Yeah.
And we overwrite the instantiation. So basically, you know, the block, the IC, it has the data width, right?
Mm-hmm.
But you know, I'm instantiating in a new environment. It's called test bench, right? So I made a new parameter because I would like to make everything generic for myself, right? I put it in the test bench, and in this guy, I can keep it change any value I want in the test bench. Let's say that I would like to test 16-bit, but you know, the block was actually 8. So why I need to make 8? I'll just go say 16. Automatically, it will generate it to be 16.
Okay.
Just like overwrite what initialized.
So regardless if you have it wrong on the test bench, it overwrites this right number.
There is nothing wrong. It's just like, you know, I would like to make a test. Let's say that, you know, I would like my circuit to be 1024-bit full adder, right? But that will be against my memory size. Then my computer will be hanging. It's better for me to say 8. Then it will map 8. If 8 work, 1024 will work. Okay. Practicing. By the way, this design is hand capped. It has a problem. Somebody can tell me what is the problem? Before to go to the problem, what is this? The last iteration of the block, it has to be generating the carryout, right? And we said we cannot write anything in the wire. Do you guys agree? Unless we force the wire to be written. And this is a new sentence. It's called what? A syntax is called assign. So which is assigning the wire to be connected with something. We force the wire to have value. So that's why this wire, which is the carry out, officially will be what? The last what? Last bridge. Do you agree?
Yeah.
Okay. The question for you guys, what is the problem with this design? Somebody tell me.
It doesn't account for overflow.
Let's see. If I say 2 here, right? So that means, you know, if I save like this, I have to go here and I found what? Two units, right? But if I say 1, what will happen? It doesn't have any problem. It works perfectly fine. I thought that, you know, when I say 1, it will not work. You understand what I'm saying?
Yeah.
See what happened? When I put 1, I agree. I just need 1 bit, right? Let's say that, you know, I would like to have 1024. Then save. Can you see? So you spend time to build logic and conceptual thing, but end of the day, this block for you is what? A piece of what? Cake, right? Now let's go to the test bench. Now I already 1024, right? But the test bench is not running 1024, by the way. If I click here, you will find that I generated a new parameter for the test bench. It's called what? Data width test bench. Do you agree, David?
Yeah.
And is equal 4. So what I did initially, this block when I initiated, right? This is basically the IC of the n-bits, right? It was written in the back of the module 1024-bit. Do you agree?
Yeah.
Yeah, but when I said this way, data width is equal this, that means I override the 1024 to be what? Just what?
4.
4. The question, why I made it here in the top, instead of going inside the file and write 4 by my hand. Which is showing you that, the level of flexibility is very high now, right? Just change one value in the top of the file, everything will be done. Sounds good? Any
The
questions?
FATB underscore nbits, what file is that? Or is that just a name or?
Just a name. You can make a new name.
All right. So the FA nbits, the first one, line 35, that's the file. The other one, right?
Mm-hmm.
All right.
Okay. Any questions so far? Joseph, do you have any question?
Can you scroll down a little bit, please?
Sure. Test bench, you forgot.
The test bench, yeah. Thank you.
Initial block, same thing, Any question regarding this subject?
Professor, is there a way to, let's say you have a lot of bits and maybe you want to simulate like a truth table through like 8 bits, like, 2 to the power of A is like a really big number. Is there a way to make like a loop or something to go through all those combinations?
Oh yeah, definitely. That's something we're gonna go through it. Yes. And instead of writing by your hand like that, yes, of course.
Awesome.
They're gonna not be for generate, it's gonna be, it's called for loop. That's it. It's gonna be a normal for loop.
Awesome.
Okay. Noah said something. Can you define wires in the generate for structure? What do you mean? Can you define wires? But Noah here, right? Look, that was the wire, right? Do you agree?
Can we use a sign?
Oh, you want to sign inside here?
No, my question is like, can we have like an assign of a array that has like ands and ors in it?
I would not recommend to do that.
Okay.
That makes sense? That's why if you notice, I took it out, right? It's better for you to make everything like looping, right? And you just take the out. You agree?
Yeah, I think.
It's like basically like you're sorting blocks by your hand, right? Don't take it at. Okay, let me tell you something. This is not a software. That's not even a software, right? That's just a way to. That's why it's called hardware description language. What's called hardware description is describing blocks connected to each other, right? So it's not the fundamental of normal software because software is using CPU. Do you agree?
Yeah.
Does it make any sense for everybody here? Any question or should I move forward? Because Joe was asking about, the board stuff, right?
Right.
Yeah. So before I go to the board, any question? Okay, if everything is clear, can you please write yes in the chat or say something or thumbs up or something?
Yes, it's pretty clear for now.
Okay. Just Christopher said clear, and then Adrian said clear, and David. That's it. What about the rest of the nation? 10 out of 4. Okay. Anyway, now the board, right? 1 bit full adder. So we're gonna go here, and okay, now I'm gonna go, and I just need one of them. So set as a top, right? It's updating. It went. Okay, perfect. Then you go here into the simulation, and you will also make it as a top, because you might need simulation, right? So don't forget, everything is possible this time. I would like to connect this IC I built, or chip, or whatever you call, into some switches on the board I have in the camera, right? You guys agree?
Yes.
So the mapper of the input output ports, it should be under what? The constraints. And that file extension is called XDC. So every single board, it has its own XDC. Because at the end of the day, the chip itself, it has an infinite number of pins, right? But the PCB board maker already assigned some of these pins to be connected to those IO devices, and some of them internally for passing some stuff, right? So XDC is made by who? Digilent. Because it's specified for the board. You guys agree?
Yes.
So I already copy, for Nexus 4A, Nexus A7, it has its own version. So you search for it, you'll find it. Mine is Nexus 4, right? So I just downloaded, and it's recorded in the video last time, right? So if you go here, you click on the XDC, you will find the file that defining LED, how you can communicate with switches, VGA, Ethernet, PMODs, Q flash, whatever, right? QPI flash, and so on. For this specific example of 1 bit full adder, right? What I need.
What was the question again? I'm sorry.
To represent the 1 bit full adder in this board, what exactly I have to use?
We need switches, right?
Exactly. Just like switches, and then present the output in LED or in something else. Whatever we learned so far is LED and switches. Do you guys agree?
Yeah.
1 second. Okay. Okay. So now how many inputs we have? 3, right? And those 3, every single one a single bit, right? Single wire, right? So I took the carry in and I connected into the first switch. Then I skipped the second one. Then I took the second, which is the A, and I connected to the third switch. Then I skipped the fourth one. Then the fifth one I connected to the third operand, right? I mean the operand into the fifth switch. So now I know that for sure this, if I look very carefully here into my board, into the camera, right? The first one again you carry in. The second will be the nothing. The third will be A. The fourth will be nothing. The fifth will be what? B. You guys agree?
Yep.
Okay. Now I need the LEDs, right? So I know that, the LED section started with LED, right? So I have 16 of them. I like to represent it in a very fancy way. So what should I do? I went into the first one and I make it to be the carry out, the sum, while the last out of 16s to be what? The carry out. So far so good? Okay. Clear? Hello?
Yeah.
Okay. Now I save to be sure that everything is done. Then I will run what? Generate bit stream. Why I click in the last one? Because the last one will make the whole stack run. Make sense? That means, you know, when I run generate bit stream, what will happen? Synthesis will be running. If synthesis pass well, run hardware implementation will be running. If run hardware implementation run perfectly fine, it will jump and generate bit stream. That's why I went in the last one just to finish, you know. But if you want to take them step by step, there is no issue. Monitoring what is going on is gonna be under design what runs. Make sense?
Yep.
Hello.
Yes, makes sense.
Okay, so if you look very carefully here, you will find that I already ran some stuff right from the last time, and it's already saved. I don't need to rerun since it's already passed very well. I can just go directly into what? Flow, open hardware manager. Okay. The cable is out. I'm sorry. So you will find now in my screen and my camera, the board is running something already saved permanently on the Q flash, which we can overwrite if you want. But anyway, if you keep your eyes on my Vivado, you'll find that I selected target, auto connect. So the Digilent driver on my PC will identify the cable that is connected to who? That chip here. And it's identified it here. Can you see it here? You look local host and it's already telling you what is the local host. Takes some time. And here's the chip. ECE3300 blah, 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 blah. Right? Now program the device. The bit stream it was from the last time generated, right? So I can just say what program. If you notice the reaction, everything was lighting on the board disappeared, right? Because now the new design already got placed on the board. Let's test. And we said, you know, the first switch is a carry in and is 1. 1, 0, 0. The output will be 0, 1, and the carry out here is 0. To see that, you know, there's something in the carry out, we have to choose another one based on the functionality we checked before, right? So we said the second is skip, the third is okay. So what turn it on here? The carry out. If you want both of them to be on, that means all of them will be high, right? So the third will be skip here, 1. So that means 1, 1, 1. So what happened? We realized the design on the board, which is matching whatever happened in what? In the simulation. Make sense? Any question? Hello?
No, I just keep getting a synthesis failed error.
You? Is it not?
What was that?
You have some errors? What?
Yeah, it's too many positional options when parsing.
It might be your XDC. You connected something XDC wrong.
Okay. I see. There were some by default on for my certain chip.
Something maybe in the XDC didn't notice. Most of the mistakes is like it's a very, very like easy mistakes to figure out.
Okay.
Look into the file very well and see what is connected, what's not connected.
Okay.
Okay. Any questions so far before I move forward to the next subject? I'm sharing now the screen, which is showing that, you know, the list of the question you guys asked. This bench we covered, set up the board we covered, analysis. Who was looking for the analysis? Christopher, right?
Yes.
What analysis you want? So the analysis in the design runs, or you want the power and other stuff?
I was hoping you'd go over like if I wanted to like look at the circuit in like a block diagram based on the design source.
Sure. So let me back into the Vivado to cover this part so I can continue with a new subject to share with you guys, okay? So everybody can see my Vivado, right? Now I don't want to deploy anything. What I would like to see, I would like to see the circuit and so on, right? So I'm closing the hardware manager. And if you guys remember, under the synthesis, there is open synthesized design. Have you seen it? Also under run implementation, the open implemented design. So after synthesis, there is a schematic you can see. After implementation, there is a schematic you can see. After synthesis, you can see the power. After the synthesis implementation, you can see the power. What is what? So there is a set of lecture I will be teaching you what is all those synthesis and implementation and what does exactly mean. But you can take it as synthesis is the first step. Hear it very carefully, okay? It's the first step to convert your code into some logic circuit. A logic. Did you hear it? Like and an or and so on and stuff like that. Then implementation, it will look into what you change into graph theory of the library inside the chip and decide matches. Then it will start doing something that's called routing. That means connect between of them. That's why you will go after that into what? Generate what? Bit stream that it will be deployed on the chip. Okay. Another thing, synthesis, it doesn't care that much about the connectivity with XDC. Did you hear it? Implementation is the first step with the XDC to be sure that you are connecting into the input-output post correct. So if some errors happen in the bit streams, you have to go back to implementation to see whether that XDC connected correct or not. Okay? Sounds good? Hello?
Yeah.
Okay, back. So, let's see the report power. I would like to see how much power I'm consuming in this and why, right? So I would say what? From the synthesis, report the power. And I say what? Open design. Because synthesis have been run before, right? So why I need to rerun it? It would take so much time. Did you see what's popped out here, Christopher?
Yes.
This is the modeling of the chip. Normally, for our stage, for our entry course like Verilog we are taking now, this is the first time ever you take Verilog, right? So you don't need to go too much into the modeling in temperatures. So you can just say, okay, which is the final setup. But, imagine that, I'm in a space, right? Industry temperature or commercial, maybe, some pressure will apply on it, right? Here, you have to change these values, like the temperature of the chip might go up or down and so on, you know what I mean? So you don't need to care that much about it. Here is the voltage even. Here is the switching, like, what is the time that you will toggle, like, on and off, how much time it will be between of them. And even, if you would like to push input and output, simulating something running in the chip and how much power will be consumed. You don't need that. So you just say what? Okay. Based on the default setup. Okay. It takes time, but it went inside here and opened a new Windows called Power. Have you seen it?
Yes.
If you grab this up a little bit, it will tell you the information. So for this specific design, if it's mapped on the chip, the total power consumed will be what? 2.815 watt. while the temperature is 37.8 Celsius. If the temperature go up or down, this might change. Sounds good? Why it say here confidence is low? Because we didn't make a real emulation. We didn't put text file, we pushed in values and see what will happen, right? We're just taking initial impression. Make sense?
Yes.
If we change a little bit, this can be changed from low to medium or high. But just take it for now like that, okay? Now it's giving you analysis. Why this 218 happened? So the 218, part of it, it was from the static device. What is the static device? Huh? Buffers. And almost 96% out of the 100% of this 218, 81, I'm sorry, is dynamic. And if you look literally, it's caused by the switches and IO, the switches and LEDs. It's taken 2.665. If we are not using that much switches and LEDs, this value can significantly go down. Did you hear what I'm saying?
See.
The rest here is the, did you see those wires and, you know, gates and whatever we use, right? The rest of the power is between of them. Why I'm telling you these detailed of details, right? Because, you know, when you design in circuit, you design for target, right? Are you building the circuit to be fast? Or are you building the circuit to be low power? Are you building the circuit to use as much as you can resources to finish your job? Or are you building the circuit to actually use less resources on the chip? Are you building the circuit to, for instance, to run with many number of cycles? Are you using this to be running in a low number of cycles? So you have to set up a target for your design. It's not just writing code for writing code. Make sense?
Yeah, that's really cool.
Another point. This board is small, right? So pretty much it's better. It's made for what? Arctic 7. Arctic 7 is a family of the chips that is for low power. So it's better for us to focus in this course and how can we use less resources on the chip, less number of lookup table, less number of input-output ports, which is mean what? Less power to consume. Do you agree? Mm-hmm. And that's gonna be our direction till the end of the semester. So far, so good?
Yes.
Perfect. Now, you ask it for the circuit, so schematic. Here is a schematic. Did you see it? It's showing you that, you know, A and B and Cn are inputs. To deal with them, you have to connect with something is called introductory buffer. I, it means input buffer, while the output is O buffer. Do something mandatory. You know, you cannot overwrite them or override them. You cannot remove them. And of course, you know, the circuit was built with a bunch of lookup tables. Let's see what we can get out of reporting power from implementation. Do you agree? So let's click here, report, and see run. Same thing, see? Okay. It gives you the same power. Have you noticed? Sometimes, the estimation from the synthesis is completely different than the estimation from the implementation. You know why? Do you have an idea why?
Honestly, I don't quite know the difference between.
I will tell you.
And
synthesis is initialization. Let me tell you something. Have you heard about something called numerical solution?
I have not.
Okay. So, I mean, in early life, they were teaching numerical in the beginning of entry for the College of Engineering. So entry, that means you in numerical solution, these tools using genetic algorithm and artificial intelligence to figure out the best way to connect between points. We call connecting between points what? Routing. You agree? So the synthesis is initial value. That means initial impression for moving this code into gates, which is initial. That means maybe after iterations and iteration, these values can be changed, right? So the iteration of the iteration until you will find the best connection between 2 points in a way that will decrease the amount of power, they call it routing, which is under implementation. So implementation is more, values of it is more accurate than synthesis. So if the implementation came and say that, synthesis were correct. But if it give you a different values, then we stick with the implementation. That makes sense?
Yeah.
Take it for now like this. Later on, I will add into it, okay?
Okay, thank you.
You're welcome. Schematic for implementation, same thing. So that means, we have the best optimization. There is no need for applying more optimization and shrinking this circuit. Any questions so far?
No, I think you answered it.
So everybody now, crystal clear for generate. Everybody now, crystal clear how to make our test bench?
Yes.
Yes.
Everybody crystal clear how can we use gate to build circuits?
Yes.
Everybody crystal clear how to communicate with switches and LEDs on board? I have a news for you. We are way advanced other sessions. You guys now reach to the point that, you are great for taking more and more into this and accomplish higher than what you have. If you fully understand what I said, you'll almost cover 7 weeks. Make sense?
Yeah.
Super. I have a news for you. Have you guys heard about an institute called EPFL? EPFL. Have you heard about it?
Not.
It's not here in the United States, in Switzerland. There's a professor, his name Unar Mutlu. So Unar, he was a professor in Carnegie Mellon. Have you guys heard about the school? CMU?
Yeah.
It's one of the top in the nation, by the way. This guy, he teach a course that's called computer architecture. Guess what material in this course he's teaching? 2300, 3300, and 4300. He combined them together in one course. Can you imagine?
Speed run.
Huh?
It's like a speed run.
Exactly. Because there is more courses. He made another course, it's called processing in memory. So he built processor inside the memory. I think he has like a 15 TA, something like that. I will find the link and I can send it to you guys for fun. You can watch it if you would like, okay? Anyway, I will stop here and we'll turn it back to what? To my tablets so we can see if we cover everything so I can move forward, all right? Everybody can see my tablet now, right? Did we cover everything? Or is any concern before I move forward? Should I move forward?
Yeah.
Okay. Now we're gonna learn about the assign and about the structure modeling. And if we have time, we're gonna move into what? Always block, which will have something is called blocking non-blocking, which will lead us into what? Behavior modeling, which is 90% of people feel comfortable with. Okay. Structure modeling. What is the structure model? Structure modeling, that means, you know, I take blocks, and I start connecting them by my hand. Or for generate. For generate, I wanted to teach you in a, like, you know, normal people teach it in a 7th week or 8th week. I wanted in the beginning, you know, I'm a reverse engineer. So then, you know, it will stick with you forever. We're gonna use it a lot, right? Then Christopher asked me about, is it possible instead of writing, is a block module or A.3 file? What is this? Mario?
Yeah. By block, do you mean like the full adder, or you mean the whole file?
Oh no,
with the code?
blocking, non-blocking is not it's not full adder. It's, I mean, it's a concept. It's something that's called blocking, non-blocking. That's basically what we're talking about here, right? I'm right, Mario?
So like, what would a block be? In
No,
the last?
blocking, non-blocking, it's a concept. Maybe I can tell you what is blocking, non-blocking now, but I will go through it later, okay? So,
Okay.
you know, blocking, non-blocking is a, you know, if you look into the clock like this is my clock, right? Sounds good? This is the clock, right? Normally the clock work in what? In this area, which is what? Positive.
Racing edge.
Rising.
Exactly. So, you know, blocking, non-blocking. Are you taking the action within the area around the edge, or you are taking it exactly on the edge?
Supposed to be exactly, right?
Exactly. So, you know, are you going to be precisely in, or you're accepting to be like, Normally people will go into within the range. You know why? Because you're giving flexibility to the synthesis and routing to the side. Because if you make it really tough, you might have something that's called what? Violation. And that will be completely covered by what? The timing lectures I will give it to you about, you know, setup time, hold the time, the slack, how to calculate the time in the maximum frequency, and bum, 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 bum. Sounds good? This specific part, 99.099999% of questions for internships and even hiring for it. Can you imagine? Have you heard about institute in Boston called the Raber?
Nope.
Okay, the Raber, it's an institute have been established by a professor from MIT. His name Michael Draper, something like that. And this institute is working for building space solution for the US Department of Defense. And they heavily hire digital engineers. And 99% of the question when they, you know, go for interview, what is the difference between setup time and hold time? What is the difference between violation, the setup time, and hold time? And they keep asking you these questions. So, you know, imagine that, you know, once you are well suited, I will ask you to try there. And, you know, if you get offer, call me. Okay. They pay like $120,000, $140,000 per year, something like that. Okay. Sounds good. Anyway, back to the future. So we need the assign, we need the structure modeling, and we need to learn the logics, symbols, and instead of writing by our hand or and then XOR, like what we did in the Git level, right? So for instance, or is like that. So you can write, assign B equal A or C. Now is ORed. Scheiße, I'm sorry. Assign, let's say F is equal A and B. Like, assign Z equal not A, that means, not gate. You see what I'm doing now? Those are the way to write the gates in the level of they call it data flow, which can be also helping us in the structure level. And instead of, write or, and you put the name of the output, then you put whatever input and you continue. That's called data flow. And you're gonna use what? Assign. So when I say assign, it's gonna be Y. You guys agree?
Yep.
For instance, XOR like this. And so on. So let me open my slides, which are gonna be extremely tired. Anyway, here, look, arithmetic operators. So in the arithmetic operators, right? So look here. Add. Did I miss something here? 1 second. Verilog, if you would like to make add in a behavior, it will be what? Add, like this. Subtract is subtract. Multiply is multiply. Divide like this. Modulus. You guys know what does modulus mean, right?
Yes.
Example for modulus, huh? It's like, 15 modulo 4. What is the output? One. Huh?
3.
3. It's a remainder, right?
Yeah, it's
Exactly, it's right. Your value, it has to be coming between 0 and 4, right? Then, exponent. What's exponent, right? 2 power 5. So this table, important for what? Behavior modeling. So far, so good. Whatever I show it to you, writing by my hand, the bitwise what? Operators. See, this is the inversion. This is the AND. This is the OR. This is the XOR. This is the XNOR. So far, so good. We are very clever people using gates, right? Do you guys agree? So I have a question for you. If I have an AND gate, it has 1 and X, what is the output? Kevin, why is X? Can you give me why it's X?
Because there's always a 1. So literally if X is 0, it's gonna be 0 and then
You're
it's
right,
1.
because if X is equal 0, the output is 0. If X is equal 1, the output is 1. So you remove this, you just put X. Right? So this table is playing this game, right? That's why they call it bitwise. But you know, the operation in the level of the bit. Bit number 1, gonna go with bit number 1. Bit number 2 will be with bit number 2. Bit 3 will be with bit 3, and so on. Cool. What about all? So bitwise level all. Did you what I said? That means imagine A is a 15-bit, and I made AND and A. What will be the output? Imagine what will happen. It will take all of these 15s and AND them together and give you the single bit out. Did you hear me? Hello?
Yes, Professor.
Perfect. Any questions so far regarding these tables I'm sharing with you guys?
So if we wanted to do a mathematic operation on like per se a parameter, we can just use the assign.
Exactly.
Okay.
Example here with assign Taylor, right? So this example is telling you that I have X, which is a 4-bit, right? And I have the output, which is 6-bit. Do you agree? Then, you know, what I'm doing, I'm just playing with wires and stuff just to apply, you know, apply what I'm learning. So I made a wire and I call it 4, and I made a wire is called Z, right? Because do you guys remember when I was talking to you last time, I said, you know, when you see the output like this, that means, you know, the wire by default. Do you guys remember that?
Yeah.
Unless what I'm gonna do, I will just write like this: out reg. Then this Z can go into the sequential, which you're gonna use always block. But you know, keep it as a secret between us. Okay. So now, if I say that, you know, Z5, that means, you know, bits 5 in Z, assign it to be equal X. What does it mean like this? It means that every single bit in X will be ANDed together, and the output will be written in bit number 5 in Z. You guys agree? Here, and with inversion, that means NAND. Here, ORing them. There, it's gonna be what? NORing them. Here, it's gonna be XORing them. You add not into it, that means ignoring them. So far, so good. Then this example showing you that, you know, I just played with instantiation just to get used to the instantiation. So I made another file. I call it what? Top file. So here is a story I need to mention to you guys. We built today, we built last time, and you know, we revised it today, full adder. You guys remember? Then, you know, we came into that full adder and we replicated multiple times using the for generate, and we build what? FA in bit. Make sense? This FA in bit is considered what? Top file. Normally in the readability for companies, right? We you know, we be sure that, you know, the highest file in the hierarchy, we call it what? Top.v. Then the module inside will be what? Top. Do you know what I'm saying? Do you understand what I'm saying or not?
Yeah.
So the FAN bit for us is what? Top V. Top file, and of course .v, right? Normally the design is not like what you are doing now. Imagine I just would like you to imagine the following, right? I build the full adder in bits. Do you guys agree? So in bit, that means, you know, I have here in bit, and I have here in bit, and I have here in bit. And then, I have here what FA like this. This is what we built, right? And this is A, and this is B. Imagine that I would like to add this into a bigger system that will what? Apply here what? A rotation. And I apply here what? A rotation. And then, I will have here the input A and input B. Do you see what I'm doing now? I'm building complicated circuit. Do you guys agree? So normally you build this component, you build this module, and then, the file will be taken all of those guys in a big picture that will be a what? Top file. So far so good? Taylor, does it make sense?
Yeah.
Okay, so that means how many instantiation I have in this in top file in this case? How many module I will instantiate from your point of view, Taylor? In this particular case,
Would we have 3 instantations?
3, you're right, because this one and this will be instantiated twice. But of course, it has 2 different names. That's why it will be considered as a different module, right?
Yeah.
Perfect. Example. Have you guys heard about something called majority encoder?
Yes.
What is the majority encoder?
Well, you have some amount of inputs, and when the number of ones is greater than zeros, the output's 1.
Did anybody told you about that before, or you know by yourself?
It was from your 2300.
Oh, you were taking with me the course. Oh, I'm
Yeah.
sorry. Yes, I'm the only one trick people with it. But anyway, imagine you would like to build this majority encoder using full adder. How are you gonna do it? That's a 2300 tricks, right? Let's simplify. Anyway, imagine that, I have a box. It's called majority encoder. It has 4 inputs, right? 1, 2, 3, 4. And those 4 inputs is 1 bit at a time. So it's majority. So the output is what? 1 bit. So you need to define, is it majority for 1 or majority for 0? If you remember 2300, if the majority for 1, that means is active what? Active high. If it's for 0, is active what? Low. Right? Example. So imagine that, it's active high, right? And here 1, 1, 1, 0. So we count how many ones I have in those guys. I have 3 versus 0. I have 1 here, right? 3 over 1, that means the output should be what? 1. But I have 4 inputs, right? So that means the truth table will be covered by how many states?
16.
16, right? Here's the 16th. And you look per state, right? So per state, 0, 0, 0, 0. 4 zeros versus none 1. The output is what? 0. 1 versus 3 zeros. 0. 1 versus 3 zeros. 1 versus 2 versus 2. 0. 1 versus 3 zeros. 2 versus 2. 0. 2 versus 2. 0. 3 ones versus 1 0. Winner. Back until you will come here, right? 3 1 versus 0. 1 1. 1 2 3. 3 1 versus 1 0. 1 1 2 3. 3 1 versus 1 0. 1. All of them 1, nothing 0. So 1. That's why it's called majority for ones, or active high 4 input majority encoder. Sounds good? That's why I put here in the side problem, design a digital circuit with a 4 inputs that will output as 1 if the majority 3 or 4 of the inputs are 1. If you would like to tackle this problem, you already built the test bench. That's why I'm telling you, 3300 is it's combination between 2300 and 3300, right? So basically what I'm doing here, I took the specification of my problem. Then I move into a truth table. Then I already set up the states. I can go into what? Either that I will go into writing my code directly, or I will go in manual optimization using K-map. Then I went into the K-map. And from the K-map, I built the polynomial or the Boolean algebra equation describing the relation between the output and the input. Do you guys agree?
Yes.
Is it clear to the rest of the nation? Or should I repeat it? If it's clear, please write clear.
It's all clear.
Perfect, thank you. Then writing code is a piece of cake. Since we learned the trick of the parameters and the parameters with assign, right? So here is my input A, B, C, D, as we mentioned in the table here. And here is my output, which is F. And here is gonna be here F, right? And we know the F is wire because we are using assign. Do you agree? Then, we're starting writing here with the gates I already learned from a couple of minutes ago, which is basically aligned with what I have from the Boolean algebra equation. And I put it here and I'm done with my task. Then, because I like to play this, if I would like to connect it LED, I want to make another instantiation. It's not needed to do it, but I just did it so I can learn the trick of instantiation as a warming up, and then, we are done. Very good question to you guys. Imagine that, I would like to build 1-bit full adder using majority encoder and 2 XOR. What should I do? So here's the task. Look at this task. 1-bit full adder using majority encoder plus 2 XOR gates. See, so I told you that I want to design 1-bit full adder, and I told you what exactly I need to use it. What exactly components I need. How are we gonna do it with Verilog? Any thought, Taylor? What should I do? How are you gonna go into this problem? What is your approach to solve this problem?
I was just looking back at some of the work from 2300, and I realized one of the questions was replace the cout with the 3-bit majority encoder.
You know the trick I asked Taylor. Sorry.
No problem. Sorry.
Taylor, do you have any idea about how we're gonna do it?
No, I wasn't sure. So.
Huh?
I'm not too sure now.
I will tell you, but I'm asking Taylor. Come on, Taylor. Taylor?
I'm not too sure.
No, you're fine. I'm just checking. So, Christopher,
Yeah.
wait until I see what happened. Mario, do you have an idea of how we're gonna fix it?
I have no idea.
Anybody than Christopher Lee know what is the trick? Before I share the trick? We are engineers. That means we have to be tricky. If your professor is tricky, you can be trickier more than him. Okay, rule number 1. We are all of us human. That means we are all of us very smart, right? So that means all of us can trick each other here, right? So if I don't know what's going on, it looks scary. Better for me to put this bench. Sorry, not this bench. A truth table. So the truth table would be like this. CN AB. sum carry out. Right? Now, since the 3 input, how many states this table would be covering?
8.
8. 1, 2, 3, 4, 5, 6, 7, 8. Correct? Then you know 0, 1, 0, 1, 0, 1, 0, 1, 1, 2, 1, 1, 1, 2, 1, 1, and 1, 2, 3, 4, 1, 2, 3, 4. Right? Now sum 0, 0, 1, 0, 1, 0, 0, 1, 1, 0, 0, 1, 0, 1, 1, 1. So far, so good? Okay, now we're gonna start looking into the outputs, right? We just have 2 outputs, you agree? So this one, straightforward, we know it's XOR and XOR, right? It's like this, right? A with B, XOR CN. And I said 2 XOR gates, so we finished that part. So what is missing? Carry out. We look into it, right? 3 zeros, output 0. 1 versus 2, 0. 1 versus 2, 0. 2 ones versus 0, 1. 2 zeros versus 1, 0. 2 ones versus 0, 1, 0, 1. 2, 1. 3, 1. What is this?
Majority.
So you can just go ahead and put like a box like this, call it majority encoder, and 3 wires, and carry out. And those 3 wires are what? A and B and CN. Voila, we finished. Right? How are we gonna write this in the Verilog? The majority encoder we built, we're gonna instantiate it in a top file, and we're gonna add this 2 XORs with the assign, or we can make them with the XOR or whatever, you know, we have Git level, and we combine this, and that will be the carry in, carry out. What do you guys think about it? Is it an easy task? Any question? Hello. Does it make any sense to anybody, or it's not clear?
Yeah, it makes sense.
Okay. So this type of questions, you know, I most likely bring, you know, so that's why I want you to be very what? Tricky. I will give you another example. Do you remember when we say that, you know, implement 1-bit full adder using multiplexers? How are we gonna do it? Or yeah, that's not really hard actually. You can do. Yeah. How can you do such a kind of design? It's multiplexer. Anyway, I think we are almost done for today, right? You know, I'm sure that you are also overwhelmed and tired. So let me see when we should actually finish for today. I suppose we've done 5:15. We have 2 minutes. So let's summarize what happened today, okay? But I want you to think with this mentality. This course is not related to any tricks than just syntax. And how can you write syntax? The rest is imagination, innovation, and whatever, you know, coming out of 2300 digital logic design. Make sense? I can tell you literally, you learn almost 80% of this Verilog, because you figure out how to use the gates, you figure out how can you use the parameters, you figure out there is a test bench, it has to be done, you figure out how to flexible design using for generate. we went through that again from the last work, and we combined it again as like a refresh to the knowledge. We also talked about what is the procedure and mechanism for the project that is going to be associated with this course and how we're going to go through it until the next week. And also we went through a tricks using this, blocks of instantiation from majority encoder to building circuit from other circuit, like, using majority encoder with associated gates to build a bigger circuit, like 1 bit full adder, or even higher, bigger than that. There was a specific question that, Taylor was answering about, when I have to file and, I would like to build like circuit that I designed by my hand, I will go ahead and instantiate it correctly and passing wires between of them and, putting the in and out in the in and out associated area for modules. Any questions so far? If everything clear since we started till now, give me a thumbs up. Are you guys enjoying this course, or we need to make any modification to make it more fun?
For the most part, it's good. I just gotta get used to Verilog.
If you have any idea about how can we make it more and more like fun so you can learn more, please let me know and we can work on it. Okay?
Sounds good.
Okay. It was my pleasure to talk to you guys. Please stay safe and God bless you. And I'm looking forward for your presentations on Monday. As I promised, by tomorrow or tonight, I think tonight will be hard. By tomorrow, I will be posting the topics for every single group in an announcement. Tonight, you know where you can find the videos, right?
You put them on Canvas, right?
Yes, in case that you are not really a fan of Canvas, right? I know that some of you guys are not. So, I'm gonna show you now in the chair. So, you go in my computers. Sorry, my CPP, not computers. Seems that I'm tired. Anyway, my CPP, you go here and, Canvas, right? And then, you go in a course. And then, we have 33 here, right? And there, we go in the modules. And under modules, you will find every single week. And under every single week, you will find whatever presentation slides that you will be there. And also, the video. So, for instance, the video here, right? If you click on it, it will open as a page and it will pass you to the video on the YouTube for the recorded lecture. So tonight I will be loading under modules week 3 with the video associated with this. Since we already have the slides from the week 2, so I don't need to put it again under week 3. Sounds good to everybody?
Yep.
Okay. God bless you. Go take rest and enjoy the rest of your evening.
Are you gonna stay in here for the office hours?
Huh?
Are you staying in this room for the office hours?
Yeah, it's the office hours start at 5:30.
Okay.
Okay. Did you already have made a time slot?
Oh no, let me go do that.
Can you do that? Yes. Okay. Thanks so much. Have a good one. Thank you. Bye-bye.
Professor.
Yes. Thank you. God bless.
Professor.
Thank you, guys. Bye.